welcome to our first video. I'm Mrs. D'Amico, and I wanted to first tell you that when you're doing these videos and you're trying to take notes, your best bet is to pause me often. You can rewind, you can replay anything that you miss at all. And if you're watching these videos while you're in class, you can always call me over for any kind of questions that you might have. But I am going to go rather fast through all these videos because I don't want to spend a whole lot of time taking up too much of your time with idle talk. So let's go ahead and get going with using measurement. The first thing that I want to talk about is the difference between accuracy versus precision. Now, accuracy is how close you are to an accepted value, you know, like what's found in the books. For instance, let's say that what's found in the books is that the item is 5.0 grams, and you're doing your measurement, and your measurement comes out to 4.9 grams, 4.8 grams, 4.7 grams. That means you're pretty accurate because the accepted value is 5.0 grams. Now, the second part here is precision. We always have these two interchanged, but they're actually quite different. Precision happens to be how close you are to all of your measurements. So if the accepted value is 5.0, but you're measuring 4.1, 4.2, and 4.3, though you're not accurate, you are precise because all of those numbers are relatively close together. So keep in mind that accurate means that you're correct, whereas precise means that you're consistent. Now, there's a way to determine how accurate you are, and it's called percent error, and there is a calculation that you can do in order to perform this. Now, notice that you have these these absolute value showing up on here, and the absolute value means that no matter what you get, you're going to have a positive number. Experimental means what did you find while you were in lab? Literature is the accepted value. Usually it's found in a book or on Google or whatever way that you're finding your actual answer. So when you post this, you're going to put your experimental value, what you found in the lab, minus your literature value, what is supposed to happen. Divide that by the literature value and multiply by 100. And then you'll get a percent error. So it kind of looks something like this. If we're trying to find the density of an object and the student in the lab finds it to be 1.40 grams per milliliter, and then the accepted value, the value that's found in the book, is 1.36 grams per milliliter, the experimental value is going to be the 1.40, and the accepted is going to be the 1.36. So you plug them in. Here's your experimental minus your accepted, what's found in the book, divide by what's accepted, found in the book, times 100, you're going to get a 2.9% error, which is great. That means you're really quite accurate. We're going to go ahead and move on to significant figures. Another term is significant digits, and it indicates the precision of your measurement, and we have talked about this in class. We talked about that if we were to use a ruler, then on our ruler, though we have our numbers and though we have our lines, there's always one estimated last digit. So you have to go one more number above what you think is comfortable. So if we have this paper clip here and we say it looks like it's past the 2, it looks like it's past 2.3, just ever so slightly, you're going to come up with whatever that estimated digit. If you think that's directly on the line, you could say that that's 2.30 centimeters and you would be okay. But if you think it's a little above the line, if you said 2.31, 2.35 centimeters, those are all acceptable values because that last estimated digit is yours, okay? All right, so here's where this comes into play. We need to be able to count our significant digits because if you ever open up your calculator, and we're going to be using our calculators a lot in this class, when you open up your calculator and you're doing all kinds of calculations, what you're going to find is a very long number. It might say something like 1.236788910, you know, whatever. It's going to go on forever. But is that necessarily true? Well, the way that we do find out what our actual value would be has to be in counting significant figures. So I'm going to show you how to do this. There are about a dozen rules in your textbook or in the textbook that you can get from the library. I've cut it down to 2. Now, I've heard of the ruling being called either the Atlantic Pacific. It means if you come in from the Atlantic side or the Pacific side. But honestly, if we really narrow this down, there's really 2 straight rules that we need to do in order to count significant figures. We're going to count every number as significant except for leading zeros, which means zeros that are at the beginning of the number, like that. And the only other time we don't count trailing zeros, these are zeros at the end of the number, is if you don't have a decimal place. So notice how this has no decimal place, 2500, no decimal place. We do not count those last 2 zeros. So let's do an example of no decimals. All 3 of these have no decimals, so we do not count trailing zeros on no decimals. So for the first one, we can count the 3 and the 4, but we can't count that trailing zero, so we would have 2 significant digits. For the next one, we can't count the trailing zeros again because the no decimal, so we can only count the 3, the 0, and the 4. So that's 3 significant digits. For problem number 3, we can count all of these digits. There are no zero rules here, so it's going to be 5 significant digits. Let's do this with decimals now. Now, with decimals, we do count the trailing zeros, but not the leading zeros. None of those zeros will count at all. So in the case of 340 with a decimal, we're going to count that trailing zero. So that means we have 3 significant digits. Same thing goes with the 30400. If there's a decimal, we count the trailing zeros. That means you have 5 significant digits. For the next one, number 3, we cannot count leading zeros. So this 0 in front does not count. We can only count the 3, the 4, the 9, the 5, and the 5. That's a total of 5 significant digits, so we can count those. Again, in problem number 4, when there's a decimal, no leading zeros. We cannot count any of those, but we can count trailing zeros. So in this case, we would have the 4 and the last trailing 0. Those 2 count, 2 significant digits. Let's do an example here. We have a decimal, we have trailing zeros, so we count them all. 4 significant digits for the first one. Next one, we don't have any leading, we don't have any trailing, we count all the numbers, 3 significant digits. For the next one, we have no decimal, cannot count trailing zeros, so we would count 3 significant figures. We do not count the trailing 0. Okay, let's go back to the other one. Next one, we have a decimal, no leading zeros. We cannot count the first 2 zeros, only the last 2 zeros. We can count the trailing, so it's 2 significant digits. Okay. Now, when we go to multiply and divide, you get to use your handy calculator. And when we calculate with significant figures, especially with multiplication and division, what we need to look for is the number with the fewest significant figures. And that determines how many significant figures we can use in our answer. So let's take a look at this problem here. If we have 28.33 grams per centimeter cubed, and then we multiply it by 3.12 centimeter cubed, we get a calculator answer that looks like this. 88.3896 grams. That's too many. We do not need that many numbers. So what we have to do is look at how many significant figures we have in our problem. This first number here, we have 4 significant digits. The second part of the problem, we have 3 significant digits. The smaller of the 2 is the 3 significant digits. Our answer, 6 significant figures. That's much too high. We need to cut it down. We need to get it down to 3 significant digits. So what we do is we count our 3 significant digits. That brings us over here to the 3. And then once we get over here to the 3, then we look at the number next to it. If it's 5 and above, we're going to give that number a shove. If it's less than 5, then we're going to leave it as it is. Since it is above 5, we're going to go ahead and give that 3 a shove. We're going to make it 88.4. So our answer, once we round to 3 significant digits, with that rounding up, it's going to be 88.4 grams. And that is what you report. From this point on, you are not going to report the entire calculator answer that you get. You're going to count how many significant digits, and then you're going to report your answers with that many significant digits. Get into this practice. This is very important. If you're adding or subtracting, things work a little bit different. In this case, we look for where the number ends before we answer our calculator answer. So let's say that you have these 2 long answers here, these 2 long numbers for your problem. Wherever the first number or whatever number ends first, that's what you're looking for. What number ends first? So see, here's where my line, it ends right here at the 8. That is where you can report your answer. So we cannot report our answer past this 5. So we have to look at the next number over. It's a 3. It's below 5, so we don't give it a shove. We leave it alone. Our answer that we're going to report is only up to that 5 because this first number here ends first. If it were the second number that ended first, then that's where we would stop with our answer. And this is only for addition subtraction. I'm going to move my picture here out of the way. So let's go ahead and do here the subtraction. Same kind of rules apply. We look for whichever answer ends first, whichever part of the problem ends first. In this case, our 421 ends first. We end actually right there at the decimal because we have to line up our decimals. That's what we're going to do. Our full calculator answer comes out to 65.58, but we can't report that whole thing. So what we need to do, draw our line right where the number ends, right at the decimal. 421 ends it. So that means our answer needs to end right here at the decimal. So we look at the number to the right. If it's 5 and above, we're going to give it a shove. And so it is, and so we will. And it'll be 66 grams. And that is what you're going to report for your answer. Pardon me, I went too fast on that slide. So we go to 66 grams, and that is all you're going to give for your answer. Now here's a couple of other special rules in the case of exact numbers. So you're counting 12 students. We don't have 12.5. We don't have 12.3. We have exactly 12 students. Counting numbers do not count towards our limiting of our significant figures. So if you have 12 students in your problem, do not make it 2 significant digits. If you have exact conversions or a 1 in any conversion, that 1 is not going to limit us to 1 significant digit, nor is this 100 centimeters going to limit us to 1 significant digit. Do not count those in your significant figures. Let's do a practice problem here. You're going to pull out your calculator. You're going to go ahead and plug this in. When you do, you're going to get a very long answer. I do not want to see you report this very long answer. What we need to do, look for which one has the smallest significant digits. This one has 5. This one has 3. Our answer is going to be in 3 significant digits. So we count 1, 2, 3. So that means we look at the number to the right. It is 5 and above. We're going to give this number a shove. Our answer is going to be 193 grams per milliliter, 3 significant digits. For adding and subtracting for this next practice, we line up our decimals, decimal, decimal. We go ahead and add like it's asking us to do. And when we do, we get this very long number. Again, you cannot report this very long number. It's not allowed. Where does the number end? It ends 2 numbers past the decimal. We draw our line. This is where our answer is going to be. We look to the right. It is less than 5, so we are not going to give it a shove. It is going to be 0.17 grams. Please do call me over if you are stuck with this at all. All right, we're going to move on now to scientific notation. In scientific notation, it's a way of writing numbers, especially very large numbers and very small numbers, because the way that we would write them, we would write 65,000 kilograms. That's a lot of numbers. So one of the things that you can do is change it into what's called scientific notation. It means you are going to move your decimal until it goes in between a regular number to the left, at least 1 to the left, and you're going to count how many decimal places it took you, how many jumps it took you to move to that decimal place. So in this case here, we have 65,000, oops, pardon me, and so we're going to move our decimal until there's 1 digit to its left. So here's where our decimal is. We're going to count 1, 2, 3, 4. We moved it 4 places to the left in order to get between the 6 and the 5. So we would write 6.5 times 10 to the 4th. Those 4 jumps become the exponent. Because it's a number, large number, and we're moving to the left, our number for our exponent is going to be positive. If our number is moving to the right, if our decimal is moving to the right, then we're going to end up with a negative exponent. And I'll show you an example of that in just a minute. So let's do some of the practice problems that are here. We are going to change these into scientific notation. Very large number, our decimal's right here. We count 1, 2, 3, 4, 5, 6. We have moved our decimal 6 places to the left. It is a large number, so we are going to have an exponent of 6. So it's going to be 2.4 times 10 to the 6th. This right here is a small number. We're moving our decimal to the right. 1, 2, 3. We're moving 3 places to the right because it's a small number. It's going to be a negative exponent. It's going to be 2.56 times 10 to the negative 3. Now let's move it back to the other way. If we have a negative number, that means we're going to move our decimal to the left because it's going to be a very small number. So we're going to assume our decimal's right here. We're going to move it 1, 2, 3, 4, 5 to the left, and when we do so, our number is going to look like this, 0.00007 instead of this. Do the same thing for here. If it's a positive exponent, you're going to move to the right. We're going to go 1, 2, 3, 4, and fill in those pockets with zeros, and when we do, we end up with 62,000 millimeters. For calculating significant digits, what we need to do is we need to multiply by using what's called our EE key or EXP key, whichever one you have in your calculator. For me, my calculator will have the EE key. It's usually found as a second button. Now, in our class, we have similar calculators, not graphing, but regular scientific calculators. And you'll need this button right here. It's called the second number right here. You're going to hit the second, and then down here is the EE key. So you may want to pause me and try to locate your EE key before you try to do these problems. When you do, you're going to key in the regular number, 5.44. You're going to hit your EXP or EE key. In my class, it's EE. And then you're going to only put in your exponent because that times 10 to the means that that's what the EE stands for. So you're only putting in your exponent. Next, you put in the function that you're going to do, which is division. And then we're going to do our regular number, 8.1. We're going to hit the EE and only our exponent of 4. And then we're going to hit our equals or enter sign. You're going to get a very large number, but again, just like with significant digits, we look for the smallest number. We do not count our times 10 to the. That does not count. This one has 3 significant digits, 5.44, 3 significant digits. 8.1 has 2 significant digits. Our answer has to be in 2 significant digits. So there's 2 ways that we could do this. We could either call it 670 with no decimal, because then the 6 and the 7 count as our number, or we can go ahead and move our decimal. If our decimal's here at the end, we're going to go ahead and move it 1, 2 places to the left. So we're going to put 6.7 times 10 to the second grams per mole. All right, and then finally, this is our last slide, I promise. Finally, we're going to talk about proportions. If y changes, that means if y goes up, then x is also going to go up if you have direct proportional. That means when one goes up, the other goes up. When one goes down, the other goes down. The numbers seem to stay similar to each other. So your graph would look something like this. It's going to go straight up. Now, if you have inverse proportion, if one number increases, another number is going to decrease, or the opposite takes place. That's inverse proportion. If you were to see that, your graph is going to look something like, let me move this over, something like this. It almost looks like a little half curve kind of thing. This is what you're going to notice when we get into nuclear. It's going to be like kind of a curve because one number is going to go up, the other is going to go down. And that is the end of our slide. Thank you for listening, and I'll see you in class.